All right, question number 14. A ball is moved from Earth to a planet that has a gravitational acceleration that is double that of Earth. How does the gravitational force on the ball when it is on the new planet compare to the gravitational force on the ball when it is on Earth? So in this situation, we're looking at two different areas where the ball would be. So this is Earth, and then this is new planet. So we know that with Earth, acceleration is acceleration due to gravity, but on this new planet, and by the way, gravity 9.81, on this new planet, gravity would be double, so 2 times 9.81 essentially. So what happens to the gravitational force? So I'm going to label that F. Gravitational acceleration, that would be acceleration due to gravity, so A of G, or it would just be G. So we can use our F equals ma equation and use that the modification of the equation, which is F of G equals mg. So this is gravitational acceleration, so G of acceleration, and this is gravitational force, so G of force, right? So gosh darn it, I ran out of space. That's great. Okay, so from here, we would use the same method that we would use in the warm-up in class, where on Earth, so the same warm-up from a few days ago, on Earth, f of g is mg, and then we're going to replace these numbers with 1. Okay, so I know that my gravitational force is going to be equal to mass, which is 1, and then gravity, which is 1. So then this is my baseline force, which is 1. So then for my planet, I'm going to do the same thing. For f of g equals mg. However, this force of gravity deals with mass that is still 1, so no change in mass, and gravity that has doubled, so 2. So then force of gravity will double. So if acceleration doubles, then force of gravity doubles. So therefore, my answer is A. So we see doubles. Half, same, 1/4, no. Okay, let's go on to the next question. Okay, so in question number 15, we're given a velocity time graph. So we know that if we take the slope of a velocity time graph, that gives us acceleration. Once again, if we take the area of a velocity time graph, that gives us position. So we are looking at this question. A 0.5 kilogram object is in free fall as it falls downward near the surface of a planet. A graph of the object's velocity as a function of time is shown. What is the force due to gravity exerted on the object by the planet? So we are trying to find force. Okay, so I know that force equals ma. I also know that force due to gravity is going to equal mg. So I know that if I find acceleration from this graph, so let's find acceleration, so we're going to find the slope. So what does m equal? That's going to be rise over 1, so so I'm going to, wow, I'm really slow. Okay, so negative 2.5. Okay, so slope is negative 2.5, therefore acceleration will be negative 2.5. So if acceleration is negative 2.5, then we can say that, so since acceleration is negative 2.5, that means gravity is going to be positive 2.5. So as you can see in recent equations, g tends to be positive, while acceleration is the one that has a direction in it. So let's go on to g. So we're going to use f of g equals mg. I know that my mass is 0.5 kilograms. It's given to me. My gravity is 2.5. So 0.5 times 2.5 is going to be 1.25. So 1.25 is going to be letter B. Number 16, a ball of mass M is found to have a weight Wx on planet X. Which of the following is a correct expression for the gravitational field strength of planet X? Gravitational field strength. That's just some fancy word for G. So if a ball has a weight of Wx, Wx is just a fancy way of saying f of g. And we know the equation for f of g is going to be mg. Well, what do you know? We need to solve for g because that's what we're trying to find. So if we solve for g, then we divide by m on both sides. If we divide by m, then g will equal force of gravity over m. And let's change the notations to how the question asks us. So W of x over m. So therefore, my answer is B. The gravitational field strength, which is G, of planet X is W of x over m. We know that it's not mg, because remember mg would equal force of gravity. We know that it's not 9.8, because this is not Earth. Planet X can have any sort of gravity that it wants. It does not have to be 9.8, unless it's on Earth. M times W, there's no way that we can get that, so it's not D. Alright, so we got a nice little Atwood's machine going on, a modified Atwood's machine. So I'm not going to read this whole thing, but I just know that friction is negligible with its other end connecting to a hanging mass. So we know also that the cart is at rest, so initially velocity would be 0 initially. And we also know that students are trying to complete this as a lab. By collecting the appropriate data, the students can determine the relationship between the acceleration of the cart and the net force. Well, we do know an equation for that, force equals ma. That's an equation that we associate force and acceleration. Which of the following graphs should the students produce to show the correct relationship? So we know that y equals mx plus b. That's just our standard format for a linear equation. So let's just go to our graphs and see what we got. So after looking at all my answer choices, I know that net force is going to be in the x position, and acceleration is going to be in the y-axis. So if I know my equation F equals ma, I'm going to label my force as x and my acceleration as y. So I know y equals mx plus b. So I'm going to try to get this equation into the y equals mx plus b format. Okay, so to do that, we're going to F equals ma. So I'm going to divide by mass on both sides because acceleration is like my pseudo y. And as you can see here, y is alone. So we want acceleration alone. So then my equation will be acceleration equals force over mass. So let's break this up and put it into our y equals mx plus b format. So acceleration is going to be 1 over m times f. So all I did was that I broke this fraction down to where I separated force from mass. It still says the same thing. So just basing off of this, I can see, I'm going to ask myself, is this linear? Is this quadratic? Is this an inverse equation? So right off the bat, I can see that it's a linear, it's going to be a linear equation. So I know that it's linear because acceleration is my y, force is my x, and 1 over m is just going to be my constant, okay? Essentially, 1 over m is going to be my slope, okay? So, or my slope, which is usually a number, okay? So that's why it's a. Number 16 looks very daunting. So a force diagram above shows a box accelerating to the right on a horizontal surface of negligible friction. Okay, negligible friction. The tension T is exerted at an angle of 30 above the horizontal. So we know that if we have an angle, then that means we can break tension into its components. If the coefficient of kinetic friction between the box and the surface, which of the following is a correct mathematical equation derived by applying Newton's second law? Alright, so I don't know why it says negligible friction, but it gives us friction, so we're just going to ignore that it says negligible friction and just continue knowing that there's friction. So T, we're going to break it into its components. So if we break it into its components, then I'm going to zoom in real quick. Okay, so if we break it into its components, we see that there's a little triangle that we can draw. So if we draw this little triangle, maybe like this. So there's my little triangle. The side that is adjacent to the angle is going to be t sine theta. The side that is, not t sine theta, cosine theta. The side opposite is going to be t sine theta because it's opposite to the angle. We know that t cosine theta is going to be positive. T sine theta is going to be also positive. So let's go back to our whole equation. So in our whole equation, we want to see that we drew our free body diagram. So we already did that. So whenever you're coming across any force problem, you should know how to write the free body diagram. Next step is that we need to use our F equals ma equation, and we're going to decide if we want to use it in the y direction or the x direction. So we have free body diagram, check. F equals ma, sum of all forces equals mass times acceleration. We're going to use x or y. So I'm going to let you know ahead of time, you're going to need to use this equation twice. One in the x direction and one in the y direction. So let's look at all the forces in the x direction. Okay, so F of x, okay, all the forces in the x direction is going to be equal to t cosine theta, because t cosine theta is going to the right and it's positive, and friction. So that means I'm going to make friction, since it's going to the left, it's going to be negative. And then I'm going to do the sum of all forces in the y direction. So the sum of all forces in the y direction, you might go into autopilot and say that, oh, it's force normal and it's mg. Duh. But don't forget about t sine theta. That's my mistake whenever I first did this problem. So force normal is going to be positive, t sine theta also positive, and mg is going to be negative. So that's my forces in the y direction. What I can do now is that I can substitute both f's with mass times acceleration. Mass times acceleration, okay? T cosine theta. Okay, I'm just bringing my problem down. And I'm going to rewrite for friction. No, I'm just going to keep it like that. Okay, and then force normal plus t sine theta minus mg. So I know that if I'm looking at my problem, it says the box is accelerating to the right. So if the box is accelerating to the right, but it never says anything about it accelerating up or down, okay? So I know it's accelerating to the right, so therefore my A in the force, all the sum of the forces in the x direction, my A is going to be some sort of number. But in the y direction, I know that my acceleration is going to be 0. Why is it going to be 0? So the box never moves up or down. Okay, so it never moves up or down, so I can safely assume that acceleration is going to be 0. Okay, so acceleration is going to be 0. And from here, what we can do is that we can rewrite our equation. Force normal plus t sine theta minus mg. So let's just keep this in our pockets real quick, and I'm going to decide to continue elaborating on my forces in the x direction. So I know that eventually, by looking at my multiple choice problems, I know that eventually I'm going to have to solve for acceleration. And just looking at my equation down here, if I'm looking at acceleration, I also see that there's force of friction here. And then since I have force of friction, then I know that I'm going to have to elaborate on my sum of all forces in the x direction. So let's elaborate on that over here. So I'm going to draw a line and just go over here. But before that I do that, I'm going to solve for acceleration by dividing by m on both sides. Then I'm going to drag it over here so I can rewrite another step. So acceleration is going to be equal to t cosine theta minus force of friction, and it's going to be all over m. Okay, so I know that much. And I also know that t cosine theta is going to be left alone. Force of friction is going to be equal to mu times force of normal over m. So mu times force of normal is going to be an equation that you should know. So force of friction is going to be equal to mu times force normal. That's the force of friction equation. You should know this. And it's also given to you on your equation sheet. And I can see that I could stop here and just declare that the answer is going to be A, because it does look like the answer is A, but it's a trick. So it's a trick. It's not A. And I was very disappointed to see why it is, because it's not A, because we need to do something with this mess. We need to do something with this. So let's just bring down our acceleration equation. So this is only part of the puzzle. T cosine theta minus mu force normal over mass. So this is what I have so far. Let's try to match some part of this equation with this equation. So something that I see similar in both equations is that there's a force of normal. There's a force of normal here. There's a force of normal here. So what I'm going to do now is that I'm going to solve for force of normal. So if I solve for force normal, then my force normal is going to be equal to mg minus t sine theta. And then I'm just going to plug it in for force normal. So let's try that out. Acceleration, mu t cosine theta minus mu mg t sine theta all over m. So let's see if anything matches that. And oh look, it's D. D is the correct answer. So I know that was a lot. Let me just recap what I did. So what I did in the beginning was that I found my trigonometric functions with tension, broke it into its components. I'm already given a free body diagram. And then for my free body diagram, I found the sum of all forces in the x and y direction. I worked on my y direction first. I determined that acceleration was going to be 0 in the y direction because the box only accelerates to the right and never goes up and down. So 0 is going to be equal to my sum of all forces. And then I just saved this equation for later to see what I need from it later. With the x direction, I determined that acceleration was not 0 because the box is accelerating and we're going to have to solve for acceleration. So I solved for acceleration, and then I brought my equations over here for more space, and then I replace force of friction with the force of friction equation, which is right here. And then from there, I looked at this equation, and I tried to see what was similar between this equation and the equation I got from the y direction. And I saw that it was force and normal. So since it was force and normal, I just solved for force normal. So whenever I solve for force normal, I just plugged it in here, and then the answer is D. An astronaut in deep space is at rest relative to a nearby space station. The astronaut needs to return to the space station. A student makes the claim, the astronaut should position its feet pointing away from the space station. So here's my space station, my International Space Station, or ISS. So astronaut face like this. Then she should repeatedly move her feet in the opposite direction to each other. I like how she made the astronaut a woman. We don't get that many women astronauts. Okay, side comment. This action will propel the astronaut towards the space station. Oh, I wrote my little dude girl the opposite direction. Okay, so she should propel, and then she will propel towards the International Space Station. Is the student correct? Right? So when we're looking at space, we're looking at a lot of stars and a whole lot of space. So whenever you propel your feet, it's not going to be like water. Because in water, you can kick against the water. If you kick against water, then the water will kick back at you. It won't really kick back at you. Then you're actually able to propel forward, okay, because you're kicking against water. In space, you're kicking against a whole lot of nothing. So therefore, you're not going to move. So it's going to be C. No, the astronaut's feet are not exerting a force on another object, so there's no external force to accelerate the astronaut towards the space station. And you can also recall that in the movies, usually, like in the movie WALL-E, WALL-E was holding a fire extinguisher to bring WALL-E back to the space station. So they were actually able to move through space with a fire extinguisher. All right, going on to the next question. Block X with mass m and block Y with mass 2m. They both have a center of mass. So we know that center of mass is going to favor the more heavier side. So this is my center of mass. It's going to be closer to 2m because it's heavier. So COM. After it's released from rest, what is the magnitude of acceleration? So I need to find first, where is my center of mass going to be? So my center of mass is going to be down and to the right. Okay, so it's going to be down and to the right. I know it's not going to be B and D. I know it is going to be down and to the right because this object, X, moves to the right. Give me a second. Okay. X moves to the right and Y moves down. So then this center of mass is going to move down and to the right. Okay, so it's going to be a little bit kind of like that. Not the most accurate, but that's going to be my center of mass. Now we have to find acceleration. So I know that since this is a modified Atwood's machine, the whole system is going to have one uniform acceleration. Okay, and we also know that using this equation, we have force equals mass over mass times acceleration. So I know that the force of my object, okay, so the net force of my object is going to be due to object Y falling down. So if object Y falls down in free fall, then my net force is going to be due to free fall. So it's going to be due to F of G equals ma. And then F of G is going to be mass of y. Okay, let's just do mg y is going to be equal to my total mass. So my total mass, which is going to be m plus 2m times acceleration. I know that so let's backtrack to force of gravity. So for y, the mass is actually 2m, not m. Okay. So 2mg is equal to 3m acceleration 2mg. So we're going to solve for acceleration now. 3m is divided on both sides. So m's cancel out. My acceleration should be 2/3 times gravity. And then my center of mass is going to be down and to the right. So that should be A, letter A. Okay, number 21. So an Atwood's machine is set up by suspending two blocks. The blocks are initially held at rest, so V naught is going to be 0 meters per second. And then we are given a time of T naught is 0 seconds, 2 seconds pass. So the change in time is going to be 2 seconds. The speed, we're trying to find the speed of the 3 kilogram block. So we're trying to find the speed of 3 kilogram block. I can't even talk. So we're going to have to find V final. Okay. So I know that if I'm given velocity, time, and eventually acceleration, I need to use my UAM equations. So my UAM equations, we do have the one for time, which is V squared equals V naught squared plus 2, oh, that is not the one for time, but I'll just finish writing it up. That's not the one for time. The one for time is going to be Y equals Y naught plus V naught T plus 1/2 of acceleration times time squared. Or we also have V equals V naught plus AT. So that one's the easy one. Okay, so let's fill in what we have. So we have V naught, which is 0. We need to find V. Time we have, that's going to be, change in time is going to be 2 seconds. But we don't have acceleration. So from this pulley system, we need to find the entire acceleration that the pulley system is going to move at. So if we need to have the entire acceleration, I'm going to analyze this system. So I know that this pulley system will move in this direction because obviously 3 kilograms is more than 2, so it's going to be moving downwards. Since it's moving downwards, I'm going to draw the free body diagram. So for the 3 kilogram block, we have tension, tension, and then force of gravity, force of gravity. So the thing about the positive direction, for tension, for the 3 kilogram block, it's going to be negative. For force of gravity, it's going to be positive because it's going in the same direction of motion. For the 2 kilogram block, tension is going to be going in the same direction as motion, so it's going to be plus T, and then force of gravity is going to be negative. So what I want to do now is that I want to just label this 1 and 2. So equations 1 and 2, equations 1, equations 2. So from here, I'm going to find the sum of all masses for each block. So if I want to find the sum of all masses for each block, then I'm going to label this 1 and label this 2 over here. So then I'm going to find the sum of all forces for the 3 kilogram block. I'm just going to label it 3 kilogram, 2 kilogram. So the 3 kilogram block is going to be equal to force of gravity minus T. And the 2 kilogram block is going to be equal to force of tension minus F of G. One thing I need to be careful of is that I need to label my symbols. So I know that my force is going to be equal to mass times acceleration. So particularly, this is going to be mass of the 3 kilogram block times acceleration. It's going to be equal to mass times the 3 kilogram block times gravity for F of G, and then that's going to be minus T. For equation number 2, we're going to replace F with ma. So if we replace F with ma, we're going to replace it with m2a, just to label that this is the 2 kilogram block. Bring down tension, and then force of gravity is going to be mg. We're going to label that this is for the 2 kilogram block. So the thing I know about Atwood's machines is that the tension is going to be the same. So the tension is the same for this particular Atwood's machine. So what I want to do now is that I want to solve for T for both equations. So if I want to solve for T, just going to bring T all to one side. So then that's going to be equal to T is equal to so m3g minus m3a. And then for equation number 2, we have m2a plus m2g. So now I'm going to set these equal to each other. So set equal. So if I set them equal to each other, so both of these equations are going to be equal to each other, and that's going to be m3g, okay, m3g, and this is the long way to do it, but you can definitely just memorize this equation, but sometimes you have to show how you got this equation. You can't just write it down. Okay, so I'm just setting them equal to each other. m2a plus m2g. So from here, I'm going to get my accelerations all on one side and my gravities all on the other side. So let's do that. So we're just going to rearrange again. So we're going to have m2g plus m3g minus m2g be equal to m2a plus m3a, just rearranging. So from here, I'm going to factor this out. So if I factor g out, so g is going to be equal to m3 minus m2. It's going to be equal to acceleration m2 plus m3. And then from here, I'm going to solve for acceleration like I wanted to from the very beginning. I know this is very lengthy. I'm getting a little bit tired of this one question, but let's pull through. So m3 plus m2. So finally, give yourself a little pat on the back. The equation should be acceleration equals gravity times m3 minus m2. m3 plus m2. So all we gotta do is that we can just plug it into our formula. So it's going to look a lot like, so let me just bring it down here. So acceleration is going to be 9.81 m3, so 3 kilograms minus 2 kilograms over 3 plus 2, and that's going to be, okay, so it's going to be 1.96 or 2 meters per second squared. So let's go back to our kinematics equation. Okay, so if we're going back to our kinematics equation, then we can say that v is equal to v naught, which is 0, plus acceleration, which is, let's just round it to 2 meters per second squared. Time is 2, so then velocity would be 4 meters per second. Okay, so essentially with these problems, all you really need to remember, instead of going through that whole process to find this equation, is to memorize this. Acceleration equals gravity times mass of the block that is falling down. So in this case is m3 minus m2. So that's the mass of the object going up over m3 plus m2. Okay, so you just have to memorize that equation. Okay, going on to this next question. So this next question uses the same scenario, except for there is a motion detector, and that is set up by suspending the two blocks connected by a string of negligible mass over a pulley. So the pulley has a negligible mass, but there is friction as it rotates. So after 1 second, the speed of the block is going to be 1.8 meters per second. So remember, acceleration is velocity over time. So in 1 second, the block accelerated at 1.8 meters per second. So acceleration is going to be 1.8 meters per second squared. We found from our equation that, from our previous question, that acceleration is supposed to be 2.0 meters per second squared. So where did that lack of acceleration go? So that lack of acceleration went into friction. So we're going to subtract our supposed acceleration minus our actual. And we're going to get 0.2 meters per second squared. So this is going to be the acceleration due to friction. Okay, so in this case, we're going to find the force of friction. And now I know that force of friction is going to be equal to mu times force normal, but in this case, it's still a force. So we can still apply the F equals MA scenario. So in case this is A, and then we need to multiply it by mass. So if we multiply 0.2 by the mass of the whole system, it's going to be 5 kilograms. Okay, so it's going to be 5 kilograms and therefore 1.0 newtons. So it's going to be 1. So again, the acceleration that is lost to friction is going to be 0.2, and then we're just going to multiply it by the mass of the whole system. So the whole system will lose this sort of force due to friction. Going on to question number 23. So a block is pulled along a surface of negligible friction by a spring scale that exerts a force of F on the block. So here's our block B. The mass of the block is 4 kilograms. The spring scale reads 10 newtons. So it's going to be pulled. Let's say it's going to be to the right, so it's going to be 10 newtons pulled. Which of the following free body diagrams can be used to show the magnitude and direction of all the forces? So if you look at your answer choices, not only do you have to know that we have the force of the spring scale, so force of the spring, and then we should also have force normal from the surface, force applied from the surface, and we should also have force of gravity because there's gravity. Not only do you need to know the accurate representation, but you need to know the magnitude of the force normal, spring force, and gravity. So right off the bat, we are given the mass of the block. So if we're given the mass of the block, we can safely assume that force of gravity is going to be equal to mg. So then m is going to be 4, g is going to be, let's just estimate 10. So F of g is going to be 40 newtons. So that's really big, 40 newtons. So 40 newtons is like 4 times 10, right? So we know that these arrows should be 4 times bigger, okay? And then this arrow should be 4 times smaller. So the only answer choice that would show that would be letter C. So let's analyze that. Okay, as you can see, force of spring is really, really small. Really small. Force normal and force of gravity are exactly 4 boxes. So 1, 2, 3, 4 away from away from the center. All right, so we have number 24. So we have a free body diagram, but note that this box is going to be on a rough surface and it's being pulled to the right at a constant speed. So if it's going to be at a constant speed, that means acceleration is not going to be speeding up or slowing down. So acceleration is going to be 0. Acceleration in the x direction. We want to find the tension of the string. So the question's already giving us a hint that the coefficient of kinetic friction is going to be dealing with friction. So we already kind of did this question in question number 18, I believe. So I'm just going to zoom through it a little bit. If you want a little bit more depth, go back to question number 18. So we got t sine, t cosine. We're going to find the sum of all forces in the x and sum of all forces in the y direction. Okay, so in the x direction we have t cosine theta minus force of friction, so I'm just going to do F for friction. In the y direction we have normal plus t sine theta minus mg. We're going to bring out our ma in the y direction, ma in the x direction, bring everything down, force normal plus t sine theta minus mg. In question 18, we determined that acceleration was 0 in the y direction because the object is not moving up or down. So 0 is going to be force normal plus t sine theta minus mg. And then in the x direction, we know that there's constant speed, so that means our acceleration should be 0. So acceleration is going to be 0. And then t cosine theta minus force of friction. So force of friction is going to be mu times force normal. So then 0 is going to be equal to t cosine theta minus mu force normal. So we have to, we can solve for t in either direction. So if we want to solve for t, we need to figure out what force normal is. Okay, so that's what the y direction is for. So in the y direction, we're going to solve for force normal. So we solve for force normal. Force normal will be equal to mg minus t sine theta. So then we're going to use this and we're going to plug it in over here. So we plug it in over there, then t cosine theta minus mu times mg minus t sine theta. So we're going to algebra this out. So we algebra this out, then let's just bring down so that we can get a little bit more space. So we're going to break this down. We have t cosine theta. We're going to do plus mu t sine theta. So I'm just breaking down that parentheses minus mu times mg. So we're going to factor out that t. So if I factor out that t, hit t by itself, t times cosine theta plus mu of sine theta, okay, minus mu of mg. So then we're going to add mu onto both sides. So t, I'm doing like quick algebra. So whenever you do algebra it out, it should be cosine theta plus mu sine theta. So this is the algebraic equation that you should have. So what you should get is going to be 0.3 times 5 times 9.81 over cosine of 30 plus 0.3 times sine of 30, and you should get 14.47 as your answer. So it's going to be A, 14.47 newtons. Number 25, so we're looking at the center of mass between these two objects. These two objects have a center of mass that favors the heavier side. So this is a center of mass, COM. So whenever these are dropped, the center of mass is going to be affected by gravity, acceleration due to gravity. We want to compare it to mass M. So mass M, whenever it drops, it's going to follow the same path. So both the center of mass and mass M are going to be affected by the same gravity. So there's not going to be a difference in the acceleration between these two parts. So therefore the answer is going to be C. Question number 26, a variation to our wonderful elevator problems. So here's the question. A diagram above shows the forces exerted. F of n represents the force applied by the child's hand on the box. So this is going to be the force by child on box. Okay. So F of g is going to be the weight of the box. F of h. What is correct about force F of h that is exerted by the box on the child's hand? So the question is asking us, what is the force of the box on the child? If you remember Newton's third law, so Newton's third law states action-reaction pairs. So whatever action denotes a equal and opposite reaction. So the force of the child on the box should be equal to the force of the box on the child. So right off the bat, I know that my force should be, my answers should at least be not C and not D. So it can be either A or B. So let's see A, where Fn does not change as the child raises the box, or B, where Fn is larger as the box is raised than when it's held. Well, what do we learn about our elevator problems? Our elevator problems really told us that the normal force, which is going to be the, like if you saw on a scale, if you read on a scale, this is going to be the readings on a scale that changes. Okay, so this is going to be the normal force that changes. It's going to be called our apparent weight. And if you recall, so we already know the answer is B because normal force should change. And if normal force does change, then F of h should change as well. But let's elaborate. So if we're looking at this box and this box is going up, that means acceleration is going to go up. So acceleration is helping the direction of motion. So therefore it's going up. And we know if acceleration is going up, therefore my normal force or my apparent weight is going to be higher than average, which is why you feel a little bit heavier when you're on an elevator and it's about to go up. So our answer would be B. Question number 17 is a gimme. So an astronaut stands on the surface of an asteroid. He jumps such that the astronaut is no longer in contact with the surface. So if the astronaut is not in contact with the surface, what kind of force cannot be neglected? So all of these forces that are lifted, we never even learned them, so it should be D. Gravity. In this case, gravity does exist, and we should not neglect it. Number 28, a moon orbits an isolated planet in deep space. Which of the following forces that the planet exerts on the moon can be considered negligible? So we already know that gravity can't be neglected. So if gravity can't be neglected, it can't be B or C. We must have gravity. Gravity is what keeps this moon in orbit because gravity provides that centripetal force. Okay? So it could be D or A. So the question is, does electric force matter? So electric force doesn't matter because it's just so far away that it can be considered negligible. Although it is true that there is electric force, but they're just so far away, we can ignore electric force. Number 29, we did this in class for a warm-up. So the masses of two moons are determined by 2m for moon A, m for moon B. So I'm just going to do a really quick rundown of this because most of us did do it for class, but we're just going to recap it. With this equation for number 29, we would use the force between two objects. So between two objects, we would use the force of gravity is equal to big G times m1, m2 over r squared. But I'm just going to replace r squared with d squared because it just makes a little bit more sense because I'm going to refer to this as distance. So if I'm looking at this equation, how does the force exerted from the planet on moon A compared to the planet on moon B? So let's look at moon A. So this is moon A, and then this is moon B. Moon. So let's just do our baseline equation. F of G is going to be equal to G, we're going to place 1. We're going to place 1, 1. Distance is going to be 1 squared. So our baseline f of G is going to be 1. So for moon A, we're going to compare moon A plus the planet. So M1 is going to be our planet mass. M2 is going to be the mass of A or B, depending on what moon we're dealing with. So let's do the force of gravity between moon A and the planet. So F of G is going to be 1. Planet mass is going to be 1. Moon A, its mass is going to be larger, so it's going to be 2. And the distance between moon A and the planet is going to be, so it's just going to be 1. Okay, so 1 squared. So F of G for moon A and the planet is going to be 2. Let's look at moon B. So F of G, we got 1. Planet mass is 1. Moon B, mass is 1. So it's going to be the same. Distance between the moon and the planet is going to be 2. So since it's 2, 2 is going to be squared. And then our answer will end up being 1/4. Difference between moon A and moon B. Obviously, moon A has the larger gravitational force. So there's a larger force of attraction. So there's a larger force of attraction, and by how much? So by how much we say 2 divided by 1/4 is going to be the same thing as 2 times 4 over 1, which is going to be 8. So by how much? 8 times. So the gravitational Earth started from the planet on moon A is going to be 8 times larger than the gravitational force on moon B. It's going to be B. Okay, an astronaut with a mass of ma is within a satellite that orbits Earth at a height of h. So let's see, we got Earth right here. We got an astronaut. Whee! Don't go into space without a suit. Is within a satellite that orbits Earth at a height of h. Earth has a mass of me, so let's do me, and a radius of e. So let's draw that radius here. So that's going to be re, which of the following is a correct expression for the gravitational force exerted on the astronaut by Earth. So this astronaut is going to be within a satellite. So astronaut in satellite. So it has a mass of a. So let's just label mass of a, and then it's at a certain height away from Earth. So probably should have labeled this guy a little bit more center, but that's okay. It still gives us the same. So the distance away from Earth is going to be by a height of h. Okay. So the gravitational force, we know F of g is going to be equal to big G times mass 1, mass 2 over distance squared. So let's see, Fg equals gravity of mass of the Earth times the mass of the astronaut over distance. So we're not going to use just Re. We're going to use Re plus h, because as you can see, the distance from the center of the Earth and the astronaut is going to be Re plus h. So that means on the bottom, we're going to say Re plus h. It's not just going to be r, and we're going to square that. So then your answer shall be C. Okay, so going on to number 31, a satellite of mass m orbits a moon of mass m in a uniform circular motion with a constant tangential speed. The gravitational field strength at a distance of r from the center of the moon is gr. The satellite is moved to a new circular orbit that is 2r from the center of the moon. What is the gravitational field strength of this new distance? So let's break this down. We know that gravitational field strength can be determined by G equals m times, let me write it down here. So gravity is going to be equal to big G times mass over r squared. So we know that the original distance was going to be r, and then it changes to 2r. So r to 2r. So this planet, oh sorry, it's a moon, so it doesn't really matter. So it's a satellite orbiting a moon, so this distance between the two, remember, is going to be center to center, is going to be distance. So let me just label it as distance. So we're going to use our warm-up strategy from a few days ago. So this is our baseline gravity. So we're going to place 1 for G, 1 for M, and 1 for R squared. So our baseline gravity would be 1. Let's see what happens when we change the radius to 2. So as you can see, it changes to 1/4. So that means we can say that the new G is going to be equal to the original G times 1/4. Okay, so it's going to be times, wait, let me write it down here. So new is going to be equal to OG times 1/4, or G over 4, which is going to be letter A. Okay, let's go on to number 32. A satellite of mass 1,000 kilograms is in circular orbit around a planet. Okay, so planet, satellite. Mass 1,000 kilograms. The centripetal acceleration of the satellite in orbit is going to be 5 meters per second. So acceleration is going to be 5 meters per second squared. What is the gravitational force exerted on the satellite by the planet? Okay, so what we need to do with this is that we know that the centripetal acceleration of the satellite is going to be due to the force of gravity. So whenever the satellite goes around the planet, the centripetal force is going to be due to the force of gravity. The centripetal acceleration of the object also represents the strength of the gravitational field at the satellite's location. So centripetal force is going to be equal to force of gravity. I already wrote that. Therefore, the following equation that I will give you is going to be used to show you, and we already know that force of gravity is going to be mass times acceleration due to gravity. So we already know the mass of the satellite is going to be 1,000 kilograms. Gravity, due to the orbit, be 5 meters per second. And look at that. This is probably the easiest question on here. So, no overthinking needed. The answer is going to be 5,000 newtons. Letter C. Number 33. No overthinking needed. So, a student determines the inertial mass of a block that is pulled across a surface using a force probe and an accelerometer, which measures acceleration. Force probe measures force. The student's data is represented. What must the student do to determine the inertial mass of that block? I think where a lot of you might be stuck at is inertial mass. So we've only dealt with mass. What the heck is an inertial mass? Inertial mass is just a fancy term for mass. So, and remember, inertia is the affinity for an object to stay in motion if it is in motion versus to stay at rest while it is at rest. So it tends to want to either stay in motion or stay at rest depending on its scenario. So inertial mass is just mass. We're given a force and acceleration graph. What do we know about force and acceleration? F equals ma. We know that acceleration is going to be in the x-axis, so let's just label x. Force is going to be in the y-axis. It's going to be y. And we need to determine the mass. Well, would you look at that? So mass is right here. Mass is going to be in the position of this y equals mx plus v equation. So I'm going to point this. So mass is going to be the same thing as this m, which this m is not mass, it's actually going to be slope. So the slope of the line is going to equal mass. Okay, so that's going to be letter B. Okay, let's go on to the next one. So number 34. Number 34, two experiments are performed on an object to determine how much the object resists a change in a state of motion while at rest and while in motion. So inertia. In the first experiment, the object is pushed with a constant known force along a horizontal surface. There is negligible friction between the surface and the object. The motion sensor is used to measure the speed of the object. In a second experiment, an object is tied to a string and pulled upward with a constant known force. A motion sensor is used to measure the speed of the object as it is pulled upwards. The student uses the data collected. Which of the following classifies the type of mass that was determined in each experiment? So we know that this object it's at rest, okay? And if it's at rest, then it wants to stay at rest. But if it's in motion, it wants to stay in motion, right? And we know that's Newton's first law, the law of inertia. So the type of mass that this one would be inertial mass. And then this mass, so the mass that is being pulled up and being affected by gravity, would be gravitational mass. Okay, so let's look at our answer choices. So that would be letter B. Number 35, we're given a position time graph. An object is thrown upwards with a speed of 20 meters per second near the surface of a planet, where the gravitational field strength is a constant magnitude of 6 newtons per kilograms. The vertical position and the vertical position versus time of the object is shown on a graph. Is the object in free fall? So, free fall. Free fall means that the only force acting on an object is gravity. So when something falls, like an object falling, it's not going to be affected by no air resistance. Okay, so we should not be having air resistance. Whenever it falls, it shouldn't be hitting like an airplane or something. It shouldn't be hitting anything. And even if it travels up, it shouldn't be hitting any birds or air resistance either. So that allows an object to be in free fall. So free fall, that really has to do with our Unit 1 kinematic equations. So whenever something is in free fall, it is experiencing gravity that is at a constant acceleration. So we see that G is going to be 6 newtons per kilograms. So if we wanted to use our UAM equations, we can use y naught, v naught, acceleration time. So then I'm going to test out my UAM equations. If my UAM equations gives the right answer that I am expecting, then it is in free fall, because UAM equations work best whenever an object is theoretically ignoring air resistance. So let's say my time is 10, because we love tens. Acceleration, remember acceleration is going to be the same thing as g, except for it has a positive or negative associated with it. So it'd be 6 newtons per kilogram. Initial velocity is 20 meters per second. We don't know final velocity. Initial height is going to be 0. And then final height is going to be 1. Oh, my bad. Initial height is 100 according to the graph, and then final height is going to be 0. So from here, 6 is going to be negative because acceleration is going down, opposite the direction of motion. So if the object is going to be thrown upwards, it's going to be experiencing a projectile path to where it goes from 100 meters to 0. So we have y equals y naught plus v naught t plus 1/2 of acceleration times squared. So y naught, y should be 0. So we're going to test to see if y is 0. So I'm not going to include this in my equation. So I have 100 plus v naught t, which is 20, times time, which is 10, plus 1/2 of acceleration, which is, in this case, -6, because gravity, and then time, which is 110, and then as you can see, y will equal 0, and then therefore the answer is A. So yes, because the only force exerted on the object is going to be a force due to gravity, so it is therefore in free fall. My UM equations are correct, and I can go to sleep at night. Okay, so let's go on to 36. So going on to 36, we did this in class. So a comet is going to be going at initial velocity, and there's a planet right there. So it has a tangential acceleration of 0. So tangential acceleration is going to be non-existent. Centripetal acceleration is going to be non-existent. Force due to gravity on the comet is going to be this much. So a comet is passing by a planet with such speed such that the comet travels in a straight line at the instant shown. The tangential acceleration, it's all shown in the table. So why does the comet not travel in a circular path? Okay, so the question is, why does it not travel in a circular path? So whenever it doesn't travel in a circular path, that means that, okay, when an object is going in a circular motion, that means there is a force of gravity that is pulling it into a circular motion. Okay, so why does this comet just surpass it and just keep going, right? So in this case, there must be another object that is probably over here, right, that is pulling it. So the comet is being pulled by this other object, let's call it O, and then planet is going to be P. So the comet is kind of a Malcolm in the middle, in that it's being pulled by this planet, and therefore the comet is going in a straight line. So it's not going to be taken into a circular path around this one planet, and that's why the answer is going to be D. Okay. Okay, going on to question number 37. A student rides a bicycle at a constant speed and radius. The force diagram for the student bicycle is shown above. The value for each force is shown in the picture. What is the acceleration of this system? So for this, we're going to draw a circle. We have this bicycle. We know that there's friction, there's gravity, there's normal force. Okay, friction is going to be like this. Force of friction. So we can see that the centripetal force, okay, so this is going to be our centripetal force, friction, that keeps it in the circle. So right now, we don't really have to think about the centripetal force equations just yet. Let's just look at the sum of all forces in the x direction. So we know that the sum of all forces in the x direction is going to be force of friction, and then that's going to be equal to, for force, we're going to replace f of x with ma of x, be equal to force of friction. Okay, so the acceleration, which is centripetal acceleration, that is causing the student bike system to move, it's going to be this acceleration here. So now what we have to do is replace force of friction. So force of friction is going to be given to us, so 250 newtons. It's going to be equal to mass times acceleration. But we don't have mass, but we do have force of gravity. So force of gravity is going to be equal to mg. Force of gravity is 500, equal to mass times gravity, which is going to be 10, just for simplifying sakes. Mass is going to be 50 kilograms. So then 50 times A equals 250. And then A should be 5. Okay, so A is going to be 5, letter C. All right, going on to our next question. So we have number 38. Number 38, it's going to be very similar, and we're going to do more practice with this, to the question that we did on Friday, just recently. So we have a string and a toy. One end of a string is attached to a ceiling while the other end is a toy. Which of the following measuring tools, when used together, could be used to determine the time that it takes for the toy to complete one revolution around the circle? So let's just think back to our problem on Friday. We know in our problem we were given the mass of this toy. We were given the length of the string. We were also given the angle at which this travels at. So we know that for angle, we need a protractor. So that's going to be one of ours. The length of the string matters. So the length of the string also matters whenever we're trying to determine the time it takes to make one whole revolution. So that would be a meter stick that we need to use. And then mass, we can use a scale, but that's not one of the choices. So it would be A and B. All right, congratulations. You've made it to the last question of the test. I mean, not the test, the midterm review. So if you made it this far, go ahead and give yourself a pat on the back, or just a little hug, or just a little cry, because, you know, physics is painful to do. But, you know, whatever you do to console yourself, I hope that this hasn't given you too much headaches. So let's do the last problem, number 39. So we have this ball and a string. We can see that the string is going to be getting smaller. So when it's getting smaller, the ball is going to be following this little path. So it follows this little path until it gets so small that it just gets small. So we want to know what happens. Okay, so what happens to the acceleration of the ball as a function of time? So as the radius of the circle decreases, while keeping the tangential speed the same, so the ball is going to be traveling in the same speed, what happens to the acceleration? So this one's going to be an easy one. Whenever radius decreases, so we have centripetal acceleration, the equation here, whenever radius decreases. So the smaller this number gets, the larger centripetal acceleration will become. So radius will have an inverse relationship with centripetal acceleration if your velocity is kept constant. So the only answer that would be correct would be letter B. You can check that off, send in your answers into AP Classroom, and go to sleep. Actually, no, you don't send in your questions because you already would have done it by now. But I hope that this helps you, and I hope that you have a happy time studying. Please do not stress out as much, and if you feel really stressed, come talk to me. I understand how stressful finals should be, but at the end of the day, you know, I still love you. You know, I don't care if you have a bad grade in physics or a good grade in physics. I just care that you enjoy this class. Anyways, that's my little sappy end of the video. It is 1:34 a.m. Miss Tran is going to sleep. Good night.